Hello everybody. So in this video, we're going to talk about parallel and series combinations of inductors and capacitors. All right, so what's the deal? So assume that we have two inductors, L1 and L2, connected in parallel this way, and we want to replace them with a single inductor L equivalent like this. Okay, so now what do I mean by replacing? Let's say the voltage across this equivalent inductor is V of t and the current going in there is I of t. And the same thing here, V of t is the voltage and I of t is the current here. Then replacing these two inductors in parallel with a single inductor means the relationship between V of t and I of t here should be exactly the same as the relationship between V of t and I of t here. Okay, so now if that is the case, that the relationship between the voltage and current it remains the same in both these cases, what that means is, let's say if there's a much bigger circuit over here, then you remove both these inductors and replace it with a single inductor L equivalent computed this way. If you do that, nothing inside this big circuit will change, right? That's what that means. So that means we can replace this parallel combination of inductors with a single inductor, and nothing else will change in the remaining part of the circuit. Okay, and in order to do that, we have to make sure the relationship between VFT and IFT remains the same. All right, so now let's do that. So what should this value be such that this relationship remains the same between the relationship between VFT and IFT? That should remain the same. Okay, so that's our goal, and we'll follow the same approach pretty much for all combinations. That means when we replace a particular combinations of inductors or capacitor with a single component, the relationship between V of t and I of t, the voltage and the current, should remain the same. That's our approach. Okay. All right. So now let's say I write a KCL equation at that node, then I get this equation here. Okay. And then I differentiate on both sides, I get this equation. Now, using the inductor equation, where if there's a voltage V of t across an inductor, voltage V of t across an inductor, and there's a current I of t going through it, then according to the inductor equation, we have V of t is the inductance times the derivative of the current. So I'll use that relationship here. So the derivative of current would be the voltage times divided by the equivalent inductance, because I of t is the current going through that inductor too. Right, now notice this V of t is also the voltage across both L1 and L2. So I will use that relation. I will use the relationship between I1 of t and V of t, and replace I1 of t, I1 prime of t using this term, and I2 prime of t using this term. Okay. Now since V of t is the same on both sides of this equation, I will cancel. I can divide the both sides of the equation by V of t, and I get this relationship. Okay, so that means when inductors are parallel, you get similar formulas as if you get for parallel resistors. So now let's see what happens if inductors are in series. Again, L1 and L2 are in series here. I want to replace it with a single inductor. Now, again, the voltage across from here to this point is V of t, and the current going in is I of t. The same thing is here too. Now, if I write a KCL in this loop, KVL, sorry, in this loop, I get V of t will be equal to V1 of t plus V2 of t. Okay. Again, according to the inductor equation, voltage V of t, over here. Let me see. So I'm applying the inductor equation here. I get V of t is equal to L equivalent times I prime of t. Now, V1 of t is a voltage across L1. So I can write V1 of t would be L1 times I prime of t, because I of t is the current going through L1, and V2 of t would be L2 times I prime of t. Okay, and then I prime of t is same on both sides of the equation, so I can divide both sides of the equation with I prime of t, and I get this equation here. Okay, now let's see parallel capacitors. Again, I have C1 and C2 in parallel here. I want to replace it with a single capacitor. Same conditions, V of t and I of t here, V of t and I of t here. All right. Now again, I write a KCL equation at that node. I get IFT is I1 plus I2. Now using the capacitor equation, I can write current is capacitance, equivalent capacitance times the voltage across the capacitor. Again, the same I1 is the current going through capacitor C1. So that should be equal to C1 times V of t. Note that V of t is the same voltage across C1 and C2. And I2 is C2 times V of t. Okay. V of t is same across both sides of the equation. So I divide it by it. So I get this relationship. Capacitors in parallel. The same thing again. I write a KVL in this loop. V of t will be V1 plus V2. Differentiate on both sides, you get this. Again, using the capacitor equation, so the derivative of the voltage would be 1 over the capacitance times the current. Note that the same current I of t is going to C1 and C2. So I can also similarly write V1 prime of t will be equal to this, V2 prime of t will be equal to this. Then I divide current on both sides, I get this equation, and that's it, right? So let's summarize, right? So if I have inductors in series, then I can replace it with the sum of them. If the inductors in parallel, I replace it with something like this. Capacitors in series, I replace it with something like this. Capacitors in parallel, I replace with a sum. Okay. Now, if you want to remember this again, remember like which combines in which way. So here is a simple, simple remembering tool. I'm writing the equations for all the three components, the IV relationships. Right? For resistors, we have V equal to IR, R times I of t. For inductor, we have V of t is equal to inductance times the derivative of the current. For capacitance, we have the derivative of the voltage is 1 over C times the current. Right? So now notice that if I have V of t on one side and I of t on the other, and the voltage on the left hand side and current on the right hand side, both for R and L we have, we have R and L, but for capacitance we have 1 over C, right? So this means R, and in fact, if you look at the derivations, we found, the reason inductors combine similar to resistor is because of this. When you put V of t on one side and the voltage on the left hand side, current on the right hand side, R and L are both on numerators and capacitor is on the denominator. This is why actually that happens. Okay, so that's basically it. So inductors combine like resistors, and capacitors basically combine the opposite way. Okay, so that's pretty much it about parallel and series combinations. One thing to notice is when you're trying to combine multiple capacitors into a single capacitor, you also have to note the initial conditions of the current or voltages. Initial conditions also have to be the same. Okay, and this is if you've solved some of the examples in the textbook, that will be clear on what the initial conditions are. Okay, so yeah, that's it.